Hello, this is Ruby. Today we're going to talk about hypothesis testing for a two-tailed test. What we're interested in is whether online instruction is effective. To evaluate the effectiveness of online instruction, we have a random sample of n equals 36 students. We're going to place those students in an online version of a traditional face-to-face mathematics class. We're also going to look at the average final exam score for this sample. That's going to be our dependent variable, and that average final exam score is equal to 76. So the sample mean equals 76. For the general population, the average sample is mu equals 71, and the population standard deviation is 18. This is a two-tailed test with an alpha of 0.05. Our first step is to identify the hypothesis. So our null hypothesis for online instruction equals 71. So this means that if nothing happens, we would expect to find 71. So that means that there would be no increase by taking a course online. There would actually also the other possibility is that there would be no decrease in taking the course online. So simply said, taking the course online would not improve your grade or make your grade worse. The alternative hypothesis is that by taking the course online, your final score would increase or decrease. So please recall that when you use a two-tailed test, we have equal and not equal are used. Those are the only two symbols that are used. Step 2 would be to identify the critical z and the statistical significance regions. You'd use your following information: the fact that you have a two-tailed test, that alpha equals 0.05. And since you have two tails, two possibilities. One is that the score is very high, or one is the score is very low. So one is positive, one is a negative tail. You're going to divide your alpha by 2. So you get 0.05 divided by 2, which equals 0.025. We're then going to look in the z table for 0.025 in the tail column to find the z value that corresponds with 0.025 in the tail. So when we look at our z column, and what we look for is 0.025, and it's in C as in canary, which is the third column. You see that 0.025 corresponds to 1.96. What you need to remember is that because there are two tails, it could either be a positive or a negative score. So that means we're going to have two z criticals. We're going to have one that's 1.96 and one that's negative 1.96. Okay, so now that we have that, we're going to go ahead and draw it out. So we see that on the positive side, we have z equals 1.96, which means that if we got a value greater than 1.96 from our computed z, we'd know we have statistical significance. Or the other alternative is we have a value less than negative 1.96, and then we'd know that we have statistical significance. So we know that in order for us to have statistical significance, the value either has to be greater than 1.96 or less than 1.96, and that would be the z value that's computed. So that's going to be our third step. We're going to compute the z value. And we're going to go ahead and add right in here a negative. So you have that's negative 1.96, so that you remember that one is positive 1.96, greater than 1.96, and one is less than negative 1.96. The third step is going to be to compute the z. So z equals the sample mean minus the population mean over the standard error. The standard error is equal to the population mean over the square root of n. So we have 18 over 36, which gives us 3. Then we go ahead and do the z computed, which equals the sample mean minus the population mean divided by 3, which equals 1.67. So clearly, if we look back, here what we see is that certainly 1.67 is not going to fall in our rejection region, because for us to be able to reject, we would have to have a z that's greater than 1.96. And then finally, we have to make our decision. So our decision is that z computed of 1.67 is not greater than the z-critical of 1.96. Thus, we do not have statistical significance. So, your conclusion would be that you do not reject the null hypothesis. You do not find any evidence to say that this statement, that mu is equal to 71, is false. And you cannot accept the alternative hypothesis because you do not find any evidence to say that mu does not equal 71 is true. So to describe this in words, we would simply say we did not find a statistical significant difference in the final exam grade for those taught online versus those taught face-to-face. So there does not appear to be any difference in grades for online versus face-to-face. Finally, the last thing here would be to do Cohen's d. And Cohen's d would be that we have the sample mean minus the population mean divided by the population standard deviation. So our sample mean is 76 minus 71. So essentially that would be 5 over 18 equals 0.27. So that would give us a small effect. So essentially we have a small effect here. The reason we do Cohen's d is to find the size of our treatment effect, and in this case it would be a very small treatment effect. Okay, so that's all for today. Thank you. Bye-bye.